Howdy y'alls, it's the Diabolic vtutor, and today we're going to be covering some more trig problems. So basically going over what we've already gone over plus a couple of additional topics, including negative arguments, arguments that are greater than 360 degrees or 2 pi, and then also interquadrant angles. So that's the plan. So here we are. Again, we've already covered the introductory trig type problems, and then we've covered the arguments. So for example, if you have sine of pi over 6, for example, in order to do a problem like this, all you need to do is either memorize the pi over 6 or convert it into degrees, however you wish. But we're going to be focusing primarily on the keeping it in radians, because radians is for the cool people, and then degrees are for the less cool people. So sticking with this one pretty much, but for those of you who are still not comfortable with the radians quite yet, 180 divided by 6 is 30, so this is basically 30 degrees right there. When we're doing such a problem, all you need to do is either memorize the unit circle. Some people take that route. I don't necessarily encourage that, because honestly I hate memorizing tedious stuff like that. But there is, no matter what path you choose, there's some sort of degree of memorization. Personally, I like to use the special right triangles, and all I do is just rotate them. That way I just memorize like memorize like 2 special right triangles, and then depending on your quadrant, you just shift it over and account for the positive, negative sides of the coordinates. And that's basically the strat, at least for me. So when we're doing a problem like this is going to be 30 degrees. I'm just going to go over the full method, I guess. So looking right here, that's 30 degrees. We're right here. We're going to be growing some sort of hypotenuse. It doesn't matter what the length is, because this one is just for a generic angle, which if you apply the trig function to some sort of angle, all it does is it gives you a ratio, and ratios are going to be reduced. So again, it doesn't matter what kind of distance I'm doing right here to generate this hypothesis. Hypothesis. What am I saying? This isn't science class. Hypotenuse. All right. So we're growing some sort of hypotenuse, and then you gotta swing it counterclockwise by convention, pi over 6, which is again 30 degrees. It's like, if this is 45, which is halfways of 90 degrees, then 30 degrees by visual sight should be like this-ish. So something like this. You know what? I don't like this. Maybe I shouldn't be using this coordinate grid. Let me move away from this. The reason why I don't want to use this coordinate grid is because it's committing to the lengths of sides, and I don't want to do that at the moment. Yeah. So let me just blot this out real quick. Okay. Okay, I just don't want to commit to any particular coordinates, so let us carry on with this thing right here. But I will have to draw the XY coordinate system, of course. You're right here. This is quadrant 1 by convention. This is quadrant 2, quadrant 3. Again, in a counterclockwise fashion for naming conventions. This is quadrant 4. Alright. And then just as a reminder, this is positive in the x direction, this is negative in the x direction, positive in the y direction, and then negative in the y direction. And then this thing is just strictly mechanics. So again, we're working with the 30-ish degrees. 30 degrees, we're starting by quote-unquote growing our hypotenuse in the x direction, the x positive direction. And then what we're going to do is we're going to swing the hypotenuse along here, keeping the pivot point right here. So just imagine this is like on a clock. one of those hands on those old analog. Wait, nobody uses analog clocks nowadays. I feel like this is irrelevant nowadays, right? Okay, well anyway, just pretend that this thing can swing like a metronome. There's like a connected point, and then there's a arm part, and then all it does is just swings back and forth like this, and this is the part that is anchored. So by that idea, this is what's happening right here. Again, we grow the hypotenuse, and then we're going to swing it over a certain number of degrees. It's based off of this one. It's 30 degrees if you like degrees. But again, this is going to be pi over 6 in terms of the radians, like this. So starting here, and then swing it over to right here. And not committing to any particular lengths, because sines, trig functions just give you ratios in the end. All right. So make note that there is some sort of positive x-coordinate contributing to the xy coordinate here, and then there is, of course, some sort of y-coordinate. So that's y spaces upwards, which is in the positive direction. And then this other thing is x moving to the right, so that's also in the positive direction. So positive, positive for this particular xy coordinate right there, at the tip of the hypotenuse that we have swung. Let me match up the colors. So that's going to be blue, and that's going to be red. Okay, so that's describing this one, and then of course this is a pi over 6, aka 30 degrees. Make sure you memorize it, or you have your table or your chart reference handy. But again, I always advise just to simply memorize this stuff. So this one right here, the ratios of a 30, 60, 90, or pi over 6, it's going to be 1 to 2 to root 3, and since this is in quadrant 1, then all the x and y's will be positive. So in other words, this is going to be a positive adjacent. It's positive root 3 adjacent. And then for the opposite, again relative to this anchoring point, the opposite is going to be plus 1 by convention. And then the hypotenuse is going to be a ratio of 2. So it's going to be 2 to 1 to root 3. Everything's positive because we're in quadrant 1, and I think that's all I want to mention about that one. So this is just drawing the triangle, sketching the triangle. You don't have to literally draw this out. You can, if you can do a very small sketch, or you could just imagine in your head, go ahead and do that, unless your teacher requires you to show full work. So 5 or 6, there it is. We're taking sine function. Sine, following the SOHCAHTOA, is opposite over hypotenuse. So what are we looking at? We're looking at opposite 1 over hypotenuse 2, so 1/2. So again, opposite is positive 1 because it goes up the y-axis, and then the hypotenuse is 2. Hypotenuses are usually positive. Sometimes you might see them negative hypotenuse, but that just tells you direction in which to grow the hypotenuse, which I might mention some other time, but that's what we're going to get for this first problem. So that's what we've already been doing, and then I think we worked on other angles as well within the quadrant, the 4-quadrant system. And just a comment on that one as well. So if there's some sort of angle theta, we've been working on particular situations where theta, wait, why is this color funny? We've been working with theta, and then the theta we've been working up to this point has been between 0 and 2 pi. So those are the only ones we've worked with. We haven't worked with any thetas beyond 2 pi, nor before 0. So that's going to be one of the main things we address today. All right. Let's clear that. So the next one we're going to be talking about is, I guess as a quick review, if we're doing cosine, for example, of 4 pi over 3. Yeah. So recall that this one right here, basically, where are we on this sort of coordinate system, right? So this one, starting from neutral position, which is right here, which is considered 0 degrees or 0 radians, depending on, again, if you prefer radians or degrees. And then this one right here is 90 degrees, or aka pi over 2. Because again, going in counterclockwise direction, this is 90 degrees. This is 0 degrees. This one right here is 180 degrees. This one right here is going to be 3 pi over 2 radians, and then from here to there, or 270 degrees, and then from here to here, extra 90, so the full circle is 360 degrees, aka 2 pi. So those are the monstrosities we're going to be dealing with. So what are we doing here? We're dealing with 4 pi over 3, which, 4 is greater than 3, so this one is exceeding pi. So we are in quadrant 3. Because, again, 4 pi over 3 is just a little bit past pi. So just to break that down, that one consists of 3 pi over 3, which is 1 full pi, plus an extra 1 pi over 3. Which means right here, that's going to be the first 3 pi over 3, but we have a spillover of pi over 3 right here. So basically something like this. So if we were to grow a hypotenuse and then we swing the hypotenuse way over here, that's going to be how we're going to form our triangle. And remember, when you form this triangle, you always bring it to the x-axis directly. 90 degrees right there. And then we have the adjacent. Again, the pivot point is always the perspective that we're taking. We're never taking this particular perspective. Never this angle right here. We're just taking this one. Always at the pivot point. So this would be opposite relative to our pivot point, our perspective, and then this is going to be adjacent relative to our pivot point. So in this situation, we have a negative adjacent because we're going to the left on the x-axis, and then for the y-coordinate it's also negative because we're going down the axis. And again, just to reiterate, the hypotenuse is almost always positive. So this is, what is this? So recall that we formed something, we formed a triangle here, but this itself is, if you convert it into degrees, it's already beyond 180 degrees. And you don't have right triangles with angles greater than 180 degrees. Yeah. Or in fact, you don't even have angles greater than 90 degrees. So that tells you something, right? So when we form this quote-unquote reference triangle, the angle here is the one we are interested in, but it is not like quote-unquote the true angle. So recall, 3 pi over 3 is half circle, or pi. And then we have a spillover, and that spillover is the reference angle right here. So pi over 3 is the angle that we're using to reference. So yes, you could just very well draw the 30, 60, 90 triangle right here, but we need the signages on this one. So again, negative adjacent, negative opposite. So what are the ratios for a 30, 60, 90 with the 60 degrees right here? The 60 degrees opens up into the intermediate side, which is root 3, and then the 30 degrees, which we're not referencing, opens up to the small side, 1. And then the hypotenuse is always going to be 2 ratio. So 1 to root 3 to 2. But that's if you just drew it without considering which quadrant we're located in which we formed this proxy triangle. Again, negative adjacent, negative, and then negative opposite, negative. So now we can answer the question dealing with the cosine of this proxy triangle. This is our reference angle. So the adjacent from that perspective is -1, and then hypotenuse is 2. So therefore, -1 adjacent over +2. Final answer. Moving on, of course, we are moving on to angles beyond what we've been covering so far, as mentioned before. So when we're thinking about angles, this is something called coterminal angles. So if you, for example, let's say you have, let's go back to degrees real quick. So suppose you have 30 degrees right here. And this is going to be the reference triangle that we're creating right here. 90 degrees, of course. So this one right here, it's a deviation. So first we grow the hypotenuse, and then we swing it over 30 degrees counterclockwise, and then we end up right there. Then, of course, there's an adjacent, and then there is an opposite, right? So that's the typical situation. But here's the thing, though. You could actually form the exact same proxy triangle, not by stopping here. So if you grow your hypotenuse, and then you swing it over, you could actually keep swinging it over. Keep swinging it over. Past 360 degrees, and then you could end up right back right here. So in order to do that, you need to first rotate a full 360 degrees. And then if you add in 30 more degrees, you actually end up where we first created the proxy triangle. So that will be 360 plus 30 degrees, which basically means it's going to be 390 degrees to get to the same location in which we first swung the hypotenuse. So that's called coterminal angle. Co meaning together. This is a very common prefix. You see it in biology as well, like codominance, or you see coevolution. So co means to, and then also in non-science words, you see it like in company or cooperate, co-op. So when you're doing co-op, you're working with someone together. So that's co, and then terminal means the suffix here, the root here is term, which means to end, right? Like terminate, or what else is there? Terminal. I just referenced its own word. So terminal, co-terminal, or like an airplane terminal, where the flight ends and then you get off the airplane, for example. So co-terminal means to terminate together at the same angle rotation. So yes, you could rotate 30 degrees, or you can rotate 390 degrees. They will both end you up in the same location. A nice way to think about it is if you were rotating on one of those spinny chairs, like you're sitting on those rotational chairs, you know what I mean? Here's the old gamer chair, right? Here's like that's like the headrest, and then here's the backing of the seat. And then here's the little armrests. And here's the base of the seat. Absolutely gorgeous. Perfect. There's a wheel here, a wheel, and a wheel. 4 wheels for stability. Perfect. Yeah. Okay. So imagine there's a gamer chair, right? So this is from kind of a 3/4 quarter view, but just imagine taking a bird's eye view. So you're looking from the top of this chair, okay? And just imagine the chair is planted right here on the origin. So imagine this. You are basically sitting in this chair. Here's your chair, and then you are facing in that particular direction, right? So, let me keep it in coordinates. So, the chair, you're facing to the right. So, in other words, your eye vision is facing in that particular direction. So, if you don't rotate, then that's a 0 degree. If you decide to rotate 90 degrees, then you're no longer facing where you were facing before, right? But if you do a full 360 degree turn, then you are back to facing the wall right here, or your computer screen. Yeah, let's say it's a computer screen. So there's your computer monitor, and then you're staring directly at the screen. That's going to be 0 degree rotation. But if you decide to do a little spinny-roo on your chair, and you spin 360 degrees, then even though you have spun 360 degrees, you have ended up exactly where you were facing before. But why stop there, right? Why not do 2 spins? So if you do 1 spin, full circle spin, which is 360 degrees, you're still facing your monitor. But if you do 2 spins, that's going to be a total of 720 degrees, right? Because each spin is 360 degrees. If you spin 360, you're back to facing the monitor. If you are doing 2 360 degrees, then you're still going to be facing the monitor in the end. So if you summate that, that's a total spin amount of 720 degrees. So you rotated that many degrees, but yet you're still facing the monitor. It's only when you deviate from a 360. If you deviate from the spin by not increments, by not multiples of 360 degrees, then you will not be facing where you were facing before. So if you do, for example, if you're sitting you're sitting in a chair right here, and then you're facing in this particular direction in the beginning, right? So if you rotate 270 degrees, then you're going to be facing downwards relative to this monitor, right? Now, what I want to say about that? Okay, let me say something else about the situation. So suppose your chair was facing off at an angle. You're facing at a 30-degree deviation from this neutral position. So that's 30 degrees. To achieve the same deviation, you can spin, again, 390 degrees, and that terminates at the exact same angle. You can do one more spin, and that's going to be 750 degrees amount of spinning to face in the same direction. So 750 degrees is coterminal because it terminates together with the 390 and with the 30 degrees. So let's look at some more angles. So if you're facing right here, right? Let's say that's going to be, what is that going to be? So this is going to be 90 degrees, and then we're going to be 30 more. So if your chair is facing neutral position at 0 degrees, and then you rotate 120 degrees, that takes you into quadrant 2. Spillover angle is going to be 30 degrees, right? Okay. So again, in order to get to this facing this particular direction, you need to rotate 120 degrees. This is the smallest rotation, smallest positive angle rotation deviation you can do from the neutral position. But if you want to be a little extra, you can spin an extra 360 degrees to still face in the same direction, angle direction, which is 120 plus 360 degrees. Which means you could spin 480 degrees if you really wanted to. And you'll still be facing in the same direction. So 480 degrees is coterminal with 120 degrees. So again, the word is co, which means together, and then termin, which is to end. So ending together, angles that end together in the same direction, facing the same direction. So all you really got to do is add 360 degrees, and those are called coterminal angles. So if you're starting with 10 degrees, for example, an angle that is coterminal to 10 degrees is any amount of 360s you can add to this one. So k is some sort of integer that you wish to pick. So for example, if you decide to add one extra spin, full circle spin, then your coterminal angle would be 370 degrees. If you want to do 2 spins, then your total amount of angle spin will be 730 degrees. So, but why stop there, right? You can do 3 spins, you can do 4 spins, you can do 10 spins if you want. So if you do 10 spins, what ends up being coterminal with the 10 degree, it's going to be 3,610 degrees, which is coterminal with this particular angle, because they end up in the same location. Of course, you'd be very dizzy if you did that. But here's the thing, though. You can also subtract 360 degrees. And when we subtract degrees, we're basically spinning in the opposite direction. So standard default spin is counterclockwise. Putting a negative degree deviation is going to be subtracting from the degree that you're interested in. So let's say we want to do, let's say you want to end up here, right? If you're following counterclockwise deviation, you're going to be spinning like this. How much total do you need to spin in order to end up right here if you're doing a counterclockwise spin from your neutral? Again, neutral is 0 degrees. you need to go 90 and then 90 and then 90 and then a little bit past 90. What is this? Let's just say it's 60 degrees, right? So in order to reach to this point in a counterclockwise lowest degree possible, it's going to be 270 plus this one, which is 330 degrees counterclockwise. But you don't have to do counterclockwise spins. You can also do clockwise spins. So why be spinning so much when you could spin slightly less, right? So the question is, if you're sitting in your swivel chair and you're facing in the neutral position at 0 degrees, how much do you need to turn to your right in order to be facing in this direction? It just needs to be 30 degrees. But by convention, you can't have a positive to denote going counterclockwise and having a positive to also denote going clockwise. So by convention, you have to put a negative if you're going clockwise spin. So again, sitting in neutral position, facing the monitor at 0 degrees. If you wish to turn, if you wish to do your swivel chair swing to the rotate to the right, then you need to do negative 30 degrees. So that'll be clockwise position. I hope that's clear. Alright, so let's just look at a few co-terminal angles and then hopefully it's going to make a lot more sense. So for example, if our base angle, if our lowest positive angle that we care about is going to be 30 degrees, then to get to all other co-terminal angles, you could add 360 degrees, any number you wish, or you can subtract any number of 360 degrees. How many 360 degrees will you be adding? You could only add whole number increments of those ones or negative increments that are integers. So only integers. So if you want to generalize the situation, there's going to be some sort of base angle that you are concerned about, and then all you need to do is add some sort of 360 variation. How many 360s are you adding? It's based off of k, where k is an integer. So this is a pretty generic way of expressing that idea. So for example, if k is equal to 1, then you're just doing one extra spin from your base angle to get to the coterminal angle. K could also be negative 3. So when k is negative, that means you're rotating clockwise to get to the same angle location. I think I'm very inconsistent in my phrasing, but hopefully it's clear. Okay. So again, if we're starting with 30 degrees, if you wish to generate some co-terminal angles, just add 360. 360 is probably the first one and the easiest one to do. You just add one 360. So 390 degrees is co-terminal with 30 degrees. Again, co means together and terminal means to end. So ending together in the same location. I don't know how to spell terminal. Terminal. Alright, there we go. So co-terminal. Again, we could also do the base angle, which is 30 degrees. We could subtract 360 degrees from that one. This is now spinning full circle in the clockwise direction, so we end up with negative 330 degrees. And that one is also coterminal with this one. And thankfully, whoever named this, whichever mathematicians named these ones, they did a good job, finally, picking good names for this one. They didn't name it after themselves, you know. Like Les Chatelier's or Euler's angle or something. Thank goodness it actually makes sense. Alright, so let's actually do some problems, and then hopefully it's going to make a lot more sense from there on. Alright, so making up some problems. Here is going to be sine. We're going to be applying the sine function to a particular angle. And we're going to do degrees first, but we're going to shift to radians shortly thereafter. So suppose we have 405 degrees. So again, applying the sine trig function to this particular angle, we're supposed to get some sort of ratio. And it's nice when you can do a quick sketch of the triangle. But unfortunately, this angle here exceeds 360 degrees, so we know that there's some spillover. So this one is going to be a non-reduced coterminal angle. So all you need to do is subtract enough 360s from it. It's not over 360 degrees by a lot, so we'll just subtract one 360 degrees to get to a more easily workable angle. So that's going to give us 45 degrees. It's positive. Keep in mind the signs. So because it's positive, that means that we're rotating and forming our reference triangle in a counterclockwise fashion. So 45 degrees, counterclockwise, we're in quadrant 1. So starting from neutral position, we're going to swing that one counterclockwise, 45 degrees, thereby ending right here. This is 45. And then we are going to take this portion right here, drop it straight towards the x-axis to form that 90 degrees. This is going to be a positive opposite. And continue on from the pivot point to this intersection location. That's also going to be positive for the adjacent. This is a classic 45, 45, 90, of course. Start to internalize these numbers, right? AKA pi over 4. What are the ratios for a 45, 45, 90 degree right triangle? It's going to be 1 to 1 to root 2. What are we doing? Sine function. It's just going to be ratio of opposite over hypotenuse. Everything's positive. So 1 over root 2, aka root 2 over 2, all positives. And that answers the question for this one right here. Positive root 2 over 2. So again, if you put 2 over root 2, oh, I'm sorry, if you kept that as 1 over root 2, that's technically correct, but it's the denominator is not rationalized. So I advise you to rationalize it, as most teachers would dock you off if you don't, unless your teacher's cool. Another sample problem, we're now going to take the tangent of negative, let's do another degree situation. So negative 420 degrees. 420? There it is. Alright, so negative means we're going to be spinning, rotating to generate our proxy triangle in a clockwise fashion. But this magnitude 420 is greater than 360. So all you need to do is reduce the magnitude of this one by adding 360 degrees. So what do we get? We get a clean negative 60 degrees, of course. I mean, for now, all you're going to see are going to be 30s, 60s, and 45s. Variants of those ones as well. So we have negative 60 degrees. What does that mean for us? That means we're going to grow the hypotenuse. We're going to swing this hypotenuse in the clockwise direction, because it's negative, by 60 degrees. So we end up here-ish, past the halfway mark. So here it is, 60 degrees. But because we swung this one negatively, make sure you put the negative here, just to keep track of that. And of course, we have this endpoint right here. Make sure we connect it straight towards the x-axis, like so. 90 degrees right there. So relative to this pivot point, this is going to be downwards down the y-axis. So this is a negative opposite. And then the adjacent is going in the positive x direction. So this is going to be positive. What are the ratios of a 30, 60, 90? It's going to be root 3 to positive 1 to positive 2. We're taking tangent. So tangent, SOHCAHTOA, opposite over adjacent. That's the opposite. And then, whoops, that's the adjacent. And we're not going to leave it like that. Make sure you clear the 1 denominator. Just keep it as a clean negative root 3. Final answer. And then we're done. So, not too bad. It's just thinking about definition of coterminal angles. If you have big numbers, and by big numbers I mean numbers that are greater than 360 or less than 360, then you just need to reduce it to make the reference triangle easier to find. More power to you if you don't need to do this. Some people don't need to do it. I unfortunately am not one of those people. Alright. So let's go over 3 more examples, and then we'll move on to something called interquadrant angles. So we haven't picked cosine yet, so let's do cosine of, now let's do radians. We're going to do, what are we going to do? Let's see, 6 plus 2 is 8, so 8 pi over 3. Again, I do suggest getting used to this, the radians if you haven't. But if you require radians for now, if you require degrees, here we go. It's going to be 8 pi over 3. This is in radians, so to convert it, it needs to be for every pi we've come across, that's going to be equivalent to 180 degrees. So cancel, cancel. Divide by 3, divide by 3. And then 8 times 60 is going to be 480 degrees. And that should be equivalent to this one, unless I goofed up somewhere. But of course, this angle here is greater than 360 degrees, so we shall take away just one 360 degrees to find the smallest possible positive coterminal angle, which is 120 degrees. So that's what we're supposed to get. But again, if we're just starting with radians and you wish to keep it in radians, then all you need to do is subtract full circle, which is going to be 2 pi. And it's kind of annoying because it is a fraction, and you're trying to take away a whole 2 pi. But that's okay. You see how the bottom, the denominator is a 3, so all you need to do is 3 times 2, which is 6. So minus 6 pi over 3. So what's 8 minus 6? It's going to be 2. So 2 pi over 3 is our coterminal smallest positive angle. So that's the true problem right here. So where are we? Well, if you redraw the coordinate system, then this is going to be in quadrant 2, because it's not quite 3 pi over 3, which is from here to there, 180 degrees. It's a little bit short. How much short is it to a full pi rotation? It's short by pi over 3. So like this. So this one is going to be 2 pi over 3. Because we are short this much to get to pi. Because 1 pi over 3 plus 2 pi over 3 gives us a full 3 pi over 3, which is half circle. Alright, but therein lies our reference triangle. It's right here. It's not this one right here, because this one exceeds 90 degrees. So we're referencing this angle right here, which is pi over 3. This is the one we're going to be used to generate the ratios. But in terms of the sides, it's going to be positive opposite, and then it's going to be a negative adjacent. Yeah. What are the ratios for this one, which is a 30, 60, 90? Well, this is the 60 right here, so this is going to be root 3. Root 3 for the opposite, and then for the adjacent is going to be negative 1. Because again, pi over 3, if you haven't memorized it, it is 60 degrees You know, you could always do quick math right here. This is only 3, so you take the 180 and divide by 3, and then you get 60, which tells you it's this one right there. So if this had been 6 instead, for example, then you just divide by 6, and then you get 30, which tells you this would be a 30 reference angle. All right, we're doing cosine, of course. Cosine is going to be adjacent is -1, and then the hypotenuse is going to be standard 2. And that's the final answer for this one right there. Moving on to 2 more problems, and then we're going to talk about interquadrant angles. Let's suppose we're doing sine again. Let's do a negative angle this time. So we're going to negative what? Let's do something wacky. I'll show you the answer first. So the answer is the reference angle that's still negative. I'm sorry, the starting angle that we're working with is going to be negative. So it's going to be 5 pi over 4 with a negative in front. So this is what we want to get to. And look how I'm going to generate the problem. I'm basically going to be subtracting multiple 2 pi's. In fact, I'm going to subtract this, which is basically 2 extra rotations. So again, this is our base clockwise rotation, and then we're going to spin around 1 more time. Let's do 2 more times, actually. Let's do 2. No, that is 2 more times. No, that's 1 more time. I'm sorry. Let's do 16 pi over 4. So this, what does that mean? That's going to be 8. That's going to be 4 pi. And if you recall, full circle is going to be 2 pi. So if you do this, if we're subtracting this extra 4 pi, we are subtracting 2 of these full circle rotations. So base spin, this is the base angle rotation, and then we're going to be spinning 2 full circles extra. So this is making the problem. So the actual problem, I'm going to simplify this and combine together, is going to be negative 21 pi over 4. That's going to be the problem. So let me delete this. So you already saw what it's supposed to be. But let us go forwards from here. Okay, so again, looking at this right here, 21 divided by 4 is 5-ish. So that's like negative 5-ish pi. We know that this one is going to be exceeding the size of a 2 pi. So we need to subtract or add multiple 2 pi's in order to get the reference, the coterminal angle, the smallest possible sized coterminal angle. So this one needs to be reduced. You know, take off those extra spins. So how many extra spins do we have? Again, you just do the quick evaluation. This is close to 20, and then 20 divided by 4 is 5. So that's close to negative 5 pi. So we need to add 2 full rotations to cancel the negative ones, that is. Alright, so we know we spun an extra 2 times, so we're going to cancel those 2 extra spins by adding 2 extra spins in the opposite direction. So it's going to be plus 2 of these 2 pi's. Simplifying this nonsense, of course, we have negative 21 pi over 4. It's going to be plus distributive property, 4 pi over 1. You are always entitled to put a number divided by 1, just to make it explicitly like a fraction. Currently, the denominators don't match up, so we're going to multiply top and bottom of that fraction by 4. Thereby getting 16 pi over 4. So once we sum those two, we're going to get negative 5 pi over 4. We know that this is the most reduced. We know that we've weeded out the extra spins, because 5 divided by 4 is 1-ish. So it's within magnitude size. The magnitude is between 0 and a 2 pi, so no extra spins. So this is a good starting point right there. You could, if you wish, you can change this into a positive direction by adding a full extra spin, plus 2 pi, if you really wanted to. I'll show you that afterwards, but let's stick with the negative spin first. Negative rotation first. So when we're doing a negative rotation, we're basically spinning clockwise. And make note that our clockwise spin is going to go past this one, because again, from here to there, that's going to be negative pi. But this one is 5, which is greater than 4, so we're past the halfway spin by a little bit. So again, half circle, clockwise is going to be negative pi. But in comparison to this one, if you wish to change it right now, it's negative 4 pi over 4. But this is not our full spin. Our full rotation is negative 5 pi over 4. So that's a spillover of negative pi over 4. So when we grow the hypotenuse and we swing it clockwise by negative, if we rotate it by negative 5 pi over 4, then we're ending up in the second quadrant right here because of that little spillover, and then our reference triangle is going to be right there. It's the halfways because it's the 45, 45, 90. The adjacent in this particular quadrant is going to be negative because we're going in the negative x direction. And then the opposite is going to be positive because we're going up the y-axis direction. So that's positive, and then this one's negative. What are the ratios? It's going to be root 2 to 1 to 1. Negative 1. Accounting for the signage, of course. So what are we doing? We're doing the sine one, so sine is just going to be opposite over hypotenuse. So it says positive 1 over positive root 2. Which sounds pretty familiar, right? I should put it right here. So it's positive, what was it again? Positive 1 over root 2. Which is in the denominator is not rationalized, so let's rationalize it real quick. So this is going to be root 2 over 2. And that's going to be it for this particular evaluation. Was that 3? I don't remember anymore. Okay, that's fine. So that was, I think that was 3 examples. Let's move on to something called the interquadrant angle. These ones are kind of funky, honestly. If you have a unit circle to reference, they're going to be in 4 key locations. So the first interquadrant, from a certain point of view, is right here. That's going to be one interquadrant angle. This is going to be another interquadrant angle. This is going to be another one, and this is going to be the third reference one, coterminal one. No, I shouldn't say coterminal. That's going to be the third one. So basically 4 coterminal angles. This is 1. Wait, I don't know why I'm misspeaking so much. Hold on. All right, let me say that more carefully. So we're covering the interquadrant angle. I guess first let's write that down. So inter means between, just like how you have interstate commerce. That's commerce between 2 separate states. Or if you have if you've taken chemistry, IMF, so you have intermolecular forces, forces that are between separate molecules. So when we have interquadrant angles, that's going to be angles that are between the quadrants. And we have quadrant 1, quadrant 2, quadrant 3, and then quadrant 4. They have their separate corners, so that's going to be, again, for quadrant 3. This is going to be for quadrant 4, right? So those particular sectors are quadrants, but if you are between those, right here, then that is a inter between quadrant here and then a quadrant there. So this is an interquadrant angle. And again, there's going to be four main ones. There's going to be this one, 1, 2, 3, 4, in no particular order. So this particular interquadrant angle is referred to as 0 in the smallest possible value. I mean, smallest magnitude value is going to be 0. And then this one right here is going to be pi over 2, or aka 90 degrees. That's going to be another interquadrant angle, smallest size positive. And then from here to there, that's going to be half circle to get to this other interquadrant angle. So this one's going to be 180 degrees, or pi. And then there's this interquadrant angle right there. It's 90 times 3, which is 270. So from here to there, the angle for that one is 270 degrees. Smallest positive representation for this angle. Here to there. AKA 3 pi over 2. And then there's going to be full circle, which takes you back to the first interquadrant angle at 0. So we can call that one 360 degrees. But that's just coterminal with that one. So it could be 0 radians, and then it could be 2 pi radians for full circle. So there you have it. You have those interquadrant angles. I guess you could say that there's just 3 of them, since full circle is the same as neutral. So why am I talking about this? Well, because now we're going to have to deal with these situations. This is going to be 0, this is going to be pi over 2. So for example, if you were tasked with finding sine of pi over 2, what is that going to be equal to, right? At this moment, this pi over 3 is nothing we are familiar with unless you've already done this somewhere else. So again, the angles that we are most familiar with at this point, pi over 3, which is going to be 60 degrees, pi over 6, 30 degrees, pi over 4, and their variance. And by variance, I mean like you have a number up here, so it could be 2 pi over 3. But in essence, this one, if you understand this one, then it just leaks over to this one, right? So this is in quadrant 1 for the 30, 60, 90. This one is in quadrant 2 for the 30, 60, 90. This one is quadrant 3 for the 30, 60, 90. And then this one is going to be in quadrant 4 for the 30, 60, 90. But these, I would just call them variants of this one. So you just have negative or positive situations happening in those ones. But in essence, the ratios are going to be the same as this one, discounting positive negatives. So for that one, this is in quadrant 1. That's going to be 30 degree reference angle. For that one, the similar ones are going to be, what was it, 5 pi over 6? That's in quadrant 2. And then 7 pi over 6, that's going to be in quadrant 3. And then we have 11 pi over 6, which is going to be in quadrant 4. But again, they're essentially the same special right triangle, just different orientations and different, which may have different signs for the negative, for the adjacents, or for the opposites. And this one, let me just list this one down real quick. So a variant of this one is going to be 3 pi over 4, 5 pi over 4, and 7 pi over 4. Those are the most basic variants. So these are the ones that we are most familiar with at this point. These ones are in the quadrants themselves, but now we have these interquadrant angles. Let me color them a little differently. So pi over 2, it's not any of those, or a variant of one of those. And then we have pi, and then we have 2 pi, and we have 0. So those ones are distinct from those ones, and these ones have their own ratios you can memorize as well. You don't have to memorize them. You can kind of reason it out by doing a rough sketch, in my opinion. So here's how we, but let me show you something first. So if we were to grow this hypotenuse, right, and then we were to swing it 45 degrees, here's where we end up. Make note that there's going to be an adjacent, and then there's going to be an opposite for this triangle, right? So this is for the 45, 45, 90 right triangle. Make note that at this point, the ratios for this one is going to be 1 to root 2 to 1. Okay? But look what happens. What if we didn't rotate this one 45 degrees? What if we just rotated it by this much? Keeping the same magnitude, of course. This is magnitude, this is a hypotenuse of length h. But if we kept that same length h, but we had a smaller rotation angle to begin with, here's what we would have ended up with, for example. So instead of swinging it all the way there, what if we just stopped it right here? We would have the same h, but the angle from here to here is going to be smaller than the first one, right? And here's something very interesting. What if I drew this opposite straight down to the x-axis? Look how this opposite compares to the previous opposite, right? So this is the first triangle that we drew. That's the 45, 45, 90. And then this is the second triangle that we've drawn with a smaller angle. Now the ratios are different. So this one is pi over 3 rotation. Pi over 6, I'm sorry, pi over 6 rotation. This opposite is shorter than that opposite. And that's for the pi over 6. So that ratio, if we're taking the sine of this one, so sine of pi over 6, right? So applying the trig function sine to the pi over 6, we're going to get a certain value. We get a certain ratio of red side, which is opposite, to hypotenuse side, which is magenta. So it's going to be red y over hypotenuse. So for that particular ratio, this ratio here is going to be smaller than the first triangle's ratio. So this is second triangle that we're checking out. And then for the first triangle, which was at the 45 degrees, the sine for that one is going to be 1. So we could express it vaguely like y over h. But since we are pointing out pi over 4 specifically, then the ratio is exactly 1 over root 2. So that's for the first triangle. That's this one right there. But for the second triangle, that one right there, we have a different ratio. For that one, the ratio is going to be 1 opposite over 2 hypotenuse. So look what has happened. So this ratio, once we rotate it to a smaller angle deviation from this neutral position, you end up with a shorter opposite, but the same size hypotenuse, which means this whole fraction is smaller than that ratio fraction. Continue on, right? What if we, instead of rotating it pi over 6, what if we rotated the hypotenuse by less than that? So we're keeping the same size hypotenuse, but we just have a smaller angle of rotation. Look how the opposite has shrunk. So this is our first triangle's opposite. This is the second triangle's opposite. This is the third triangle's opposite. Notice that the opposites are shrinking over time, but we're maintaining a consistent hypotenuse. You can see where this is going, right? So if we have an even smaller rotation, but maintaining the same hypotenuse, we're going to get an even smaller opposite, but the same size hypotenuse. The hypotenuse is still going to be the same size as before, right? I guess I'm being inconsistent in my numbers right here. So let's ignore the numbers. Let's just look at it visually from a qualitative perspective. So my point with this illustration is that when you rotate it from here to there, you get this high of an opposite. But if you rotate from here to there, maintaining the same magnitude for the hypotenuse, you get a smaller opposite. So what this means is that the smaller angle we have from here to here, if that angle we're doing is smaller and smaller, then the opposite becomes smaller. And when the opposite becomes smaller, then the ratio of opposite relative to hypotenuse is also shrinking. So the point of this is, what if you collapse the opposite, right? What if the opposite, you no longer have an opposite, you make it 0? You can kind of see where that ends up. It ends up right there. So at this particular angle, there's still an opposite, the red opposite, right? But for a smaller one, you have a smaller angle, you have a smaller opposite. But what if we have no opposite, which means no angle rotation? So at the neutral 0 degrees, if you never swung this hypotenuse, then you will quote unquote not have an opposite. The opposite will be 0. So to symbolically, to represent that, I'm just going to put a red dot, but just be aware that that's not going to be a height. So the opposite there is going to be 0. So in effect, it's kind of like having a collapsed triangle. Here's the visual, right? That's dissected from here. So for this picture right here, the angle here is not 0, so you still have an opposite. If we collapse the hypotenuse, if we maintain it in neutral position, it's going to be the same location as this blue part right here. We have no red. So in this situation, the opposite, which again, I'm representing with this red dot, but just be aware it's going to be 0. So opposite is 0. And then something else very interesting happens as well. What ends up happening is, look what happens from the first one. So this is going to be the first triangle's opposite. This is the corresponding adjacent. This is the second triangle's opposite. This is the second triangle's corresponding adjacent. It got longer than what it was before, right? So compare. This is for the first triangle for the 45, 45, 90. The adjacent is that long. If you look at the second triangle for the 30, 60, 90, the adjacent is longer than before. And if you look at the third triangle, that's this one right here, the adjacent is that long. So the adjacents are getting longer and longer as we are shrinking this angle of rotation, right? So what if we shrunk it all the way? What if we don't have a rotation and we're still in the neutral position with an opposite that doesn't exist, quote unquote? That means that the adjacent is going to be converged with the hypotenuse. So at this point, the length of the adjacent eventually matches the length of the hypotenuse once we quote unquote close and have this collapsed triangle. So here we still have a real triangle, right? This is still, most people would agree that that's called a triangle. And then right here, this is just a segment. That's just a line segment. Most people wouldn't call this a triangle, but we can think about it kind of like a collapsed triangle. The opposite has become 0, so the whole thing collapsed. And I don't know if anyone else calls it a collapsed triangle, but I'm going to call it a collapsed triangle, where the opposite is 0, but again, the adjacent becomes the same length as the hypotenuse. So let's write this down for this collapsed triangle scenario. So for this interquadrant angle that resulted from a collapsed triangle, there are a few things to make note of. Number one, the adjacent has become the same length as the hypotenuse. Let's do congruency signs. Let's go back to geometry. So again, for the collapsed triangle, the adjacent is congruent to the hypotenuse side. And then we also make note that the opposite is going to be non-existent or 0. Because again, it's collapsed. You didn't do a rotation, you didn't open up the triangle. So when you don't open up the triangle, then the opposite doesn't exist from this perspective. So in the event that we're trying to evaluate something like sine of 0 degrees, for example, what are we looking at? So when you have 0 degrees, then we are in neutral position. When you are in neutral position, there's been no swing. Since there's no swing, you're not going to generate an opposite side. Because there's no opposite side, the opposite side is 0. So therefore, ratio is 0 to hypotenuse. We don't care what the hypotenuse is as long as it's not 0. So 0 divided by not 0 is going to give us 0. And that's how we evaluate sine of this 0 interquadrant angle. The ratio is 0 to whatever. That's it. So the idea of having a collapsed triangle. Alright, so that's if we have a 0 degrees for the interquadrant angle. What happens when we have this particular interquadrant angle? So let's see what happens. So here's hypotenuse. If we leave it in neutral position, there is no opposite. But if we swing it this way, then we will have kind of a short opposite, right? But if we swung it this way, same ideas as before, we generate this new triangle, and this new triangle has a longer opposite right here compared to the other triangle. So you see what's happening? So if we keep swinging it, same size hypotenuse, look what happens to the opposite. The opposites are now getting longer. So this is the first opposite that we can see visually. This is the second opposite. This is going to be the third opposite. So what happens when we keep swinging this particular hypotenuse to the interquadrant angle location? Like right here. Look what happens. So from the end of the hypotenuse that we've drawn, in order to quote-unquote form the triangle, we drop it towards the x-axis. But if you notice, we're tracing the hypotenuse exactly in order to draw the opposite. So in this situation, the reverse thing has happened. The hypotenuse length becomes congruent with the, let me say that the other way around. The opposite side has become congruent with the length, with the hypotenuse. So hypotenuse is going to be congruent with the opposite. Oh, I mixed my colors, that's why I'm so confused. So, opposite. It became congruent with the hypotenuse. Again, this is all about just trending patterns in mathematics, right? So for the vast majority of your math career, when you're still in high school and such, you're just going to be dealing with basic trends like this one. So the trend is the opposites are getting longer as you are rotating in that direction to this interquadrant angle. So opposite number 1, opposite number 2, opposite number 3, opposite number 4. So opposite converges with hypotenuse. And then, of course, the inverse thing is going to be happening with the adjacent. So if you have neutral position, the adjacent is congruent with the opposite. But if we have triangle number 1, right there, with this particular angle, the adjacent has shortened by that much. If you look at the triangle number 3, then the adjacent has shortened by that much. So you can see that the adjacents are getting shorter and shorter. And when we look at this triangle, the adjacent is that long, is that short. And then finally, on the collapsed triangle, there is no more adjacent. So we say that the adjacent is just 0. There's no adjacent. There's the other type of collapsed triangle. Right there. So that's interquadrant angle at the pi over 2. So what does this mean for us? Let's do an example. So if you're doing cosine of pi over 2, what are we doing? Pi over 2 is 90 degrees, so we're rotating from here to there to form our reference triangle. It's quote-unquote a triangle, right? But it's a collapsed triangle where the adjacent has become 0. And since cosine of an angle is supposed to give us the ratio of adjacent to hypotenuse, what's the adjacent? Nothing. There's no adjacent, 0, right? Collapsed triangle. And then the hypotenuse exists. So it's some sort of positive value. So 0 over anything positive is going to give us 0. Here's another example. So if we're doing sine of pi over 2, what is that going to equal to? So same situation as what we just looked at. It's going to be 90 degrees pi over 2. So which interquadrant angle are we looking at? This is going to be neutral position. This is going to be 90-degree rotation counterclockwise. So this one is the pi over 2. So interquadrant angle, it's between quadrant number 1 and quadrant number 2. And just to colorize things to make it for visual clarity, color it purple, and then that resides right there between the two quadrants. So this is a collapsed triangle situation. What kind of collapsed triangle is it? Well, there's no x going that way, and there's no x going that way. It's a 0x coordinate, so there's no adjacent. But here is where the opposite converges with the hypotenuse. What does sine do? It gives us the ratio of opposite over hypotenuse. And since the opposite has converged with the hypotenuse, then it's going to be a 1-to-1 ratio. Or in other words, this is going to be 1. So sine of interquadrant angle pi over 2 is going to give us a ratio of 1-to-1, which is right there. And that's it. That's all you got to do. Let's look at another situation. We're going to keep it as a sine function. What if we're doing sine of 3 pi over 2, right? 3 pi over 2. So what's happening right here? Well, first figure out which of those inner quadrants we're on. We're not on the neutral position. That will be 0 or 2 pi. We're not there. So 90 degrees? No, this is not pi over 2. 180 degrees? No, that's not pi. That's 3 pi over 2. So we are right there for the interquadrant angle. So this one right here. So that's a collapsed triangle situation. But what kind of collapsed triangle? Has the opposite collapsed to nothingness, or has the adjacent collapsed, quote-unquote collapsed to nothingness? It's the adjacent that is collapsed to nothingness. So here, the hypotenuse, the opposite converges with the hypotenuse. So we can say, for this particular interquadrant angle, the magnitude of the opposite has converged with the magnitude of the hypotenuse. So the opposite to the hypotenuse, it has become 1-to-1. But unfortunately, the 1-to-1 is not the answer, because we have to take into account the y-axis upwards or downwards. And since we're going down the y-axis, then you have to say for directionality's sake, you have to put this negative sign on the opposite. So therefore, it's negative 1 over 1. So clean up, final answer is therefore negative 1. And that's the evaluation for this one right here. Because again, we have the quote-unquote collapsed triangle pointing downwards, down the y-axis. So you need to denote that symbolically with the negative sign in front. So negative 1. Negative for the downwards interquadrant angle, quote-unquote downwards. And then 1 to 1 because the opposite length has converged onto the hypotenuse length. So 1 to 1 ratio. Since we skipped it, we might as well do it, right? So what if we have sine of, let's do negative this time, so negative pi. What does that equal to? Well, which of those 4 interquadrant angles are we dealing with? Are we dealing with the 0? Nope. Are we dealing with the... Well, since this is negative, we have to go clockwise. Are we dealing with this one right here? No, that's negative pi over 2. Or negative 90 degrees. That's negative pi. Pi is half circle. So thus, we're going to be ending up right there at this interquadrant angle. Visually, I like to draw it like this. As a collapsed triangle. I just put this sideways T thing, right? Alright, so what do we acknowledge for this situation? We acknowledge that it's a quote-unquote collapsed triangle. What has collapsed? It's the opposite that has collapsed. Because again, the idea is if we grow a hypotenuse and then we swing it this way, it's already connected to the x-axis. So there's nothing to draw. So opposite is 0. The hypotenuse still exists though. So we have 0 opposite, but the hypotenuse still exists. We'll consider it positive. So 0 over positive is going to be 0. That's the final answer. So this thing evaluates to that. Because the opposite is a collapsed 0, and then the hypotenuse still exists. So 0. Let's do tangent. It's just to see what happens. So if we're doing tangent of something like negative 3 pi, well, we're doing interquadrant, I'm sorry, negative 3 pi over 2. So if you don't like dealing with negative angles, you could always change it to the smallest possible positive angle. So again, if you don't like negative angles, all you need to do is add 2 pi. And I'll change it to the smallest possible positive one if the magnitude is within 2 pi to 0, right? So adding 2 pi, unfortunately, the denominators are mismatched. So this one needs to be plus 4 pi over 2 to get to the positive coterminal angle. So once you summate that, you see that it's just going to be tangent of pi over 2. There we go. So we have rephrased the problem from this negative angle argument into this positive angle argument. But they're the same problem. So again, if you don't like negative, you could always change it to positive. So here we are. Pi over 2. Hopefully by now we know where that particular collapsed triangle lies. It lies right here, the pointing upwards looking one. So there's the hypotenuse. It's the collapsed triangle yet again. What kind of collapsed triangle? Well, since it points upwards on the y-axis, then the opposite exists. Since we're neither moving left or right from this position from the origin, so for the adjacent is going to be 0. And again, here the opposite has converged with the hypotenuse. So opposite is congruent. But what exactly are we doing when we're using the tangent trig function? Trig function in tangent is supposed to give us opposite over adjacent. So what's the opposite? It's some number. It matches the hypotenuse. And it's going upward, so it's positive. And here's the funky part. Since the adjacent is 0, we're dividing by 0. Division by 0, right? Can't do it. So unfortunately, or fortunately, depending on how you view it, right? We can't do this one, so it's going to be undefined. Cannot divide by 0. Don't put the exclamation point. So we'll just leave it like this. So for tangent of pi over 2, it's going to be some sort of positive opposite over 0 adjacent. Therefore, undefined. So going back to the original expression, we evaluate that to be undefined. Because adjacent is 0, and you divide by 0, it's undefined. There it is. Let's do a tangent that is defined, right? So if we're doing tangent of something like negative 3 pi. How do we evaluate this? Number 1, make note of this magnitude. The magnitude is 3 pi, which lies outside of the 0 to 2 pi situation. So this one is reducible. So to reduce it, all we need to do is bring the magnitude down. We have a negative situation, so you add a full 2 pi. And that will negate some of the spin, so we therefore get a leftover of just negative pi. So this is our problem. We've rephrased it from here to there. So what's negative pi? Grow our hypotenuse in the positive x direction, and we're going to swing it in the clockwise because of this negative sign into pi, which is half circle right here. So we end up right here for the quote-unquote triangle. It's a collapsed triangle. What kind of collapsed triangle? The one with the collapsed opposite. So opposite is going to be 0, and the adjacent is going to be matching up with the hypotenuse. So the adjacent exists, but the opposite will also exist, but it's just going to be 0. So we have 0 over adjacent, and adjacent is not 0. So we can evaluate that, and so we're going to get a 0 situation. So tangent of negative pi will give us a ratio of 0 to something that's not 0. So final evaluation, 0. Because again, the opposite is 0. 0 over anything not 0, it's 0. Let me pour some more tea real quick. Or I mean hot water. Alright, which takes us to the main bulk of problems. We're going to start off with the easier problems first. This is going to be straightforward evaluation. Not going to be too many steps. Basically, it's going to be some sort of trig function. There's going to be some sort of argument. No variables here. It's just an actual a known value. And all we have to do is evaluate. Alright, so first problem here. This is not interquadrant because the denominator is a familiar face, right? Familiar denominators are 3, 4, and 6. Anytime you see those ones, those are your special right triangles. Those are your 30, 60, 90s, and those ones are your 45, 45, 90s. So this is just a 45, 45 style special right triangle. Which quadrant? We're past pi, leaking into quadrant number 3. It's going to be a 45, 45, 90. It's in the negative x direction, so it's negative adjacent. It's downwards the y-axis, so it's negative opposite. Sine is just going to be opposite over hypotenuse. So the ratio is negative 1 to positive root 2. So negative 1 over positive root 2. And that's it if you want to leave it like that. But rationalizing the denominator, it's going to be negative root 2 over 2. So that's it for that one. So if it had been negative, let's just switch the sign real quick. So if we have a negative argument, but it's the same magnitude, So we have negative 5 pi over 4. It's pretty much the same style. It's just that we're moving it in a in a clockwise fashion. So again, this is how I do the problems. If I'm doing a problem like this one, first, where are we? We're going to be in which quadrant? It's going to be clockwise movement. So we're past half circle because it's 5 is greater than 4, which means we're in quadrant 2. This is 45, 45, 90 style, so we're right here. We have a negative adjacent, and then we have a positive opposite. Sign is going to be positive, and then the hypotenuse is just root 2 as a ratio, right? So the ratio is going to be 1 to root 2, which rationalization is going to be root 2 over 2. Next up, we have cosine of negative 2 pi over 3. It's going to be one of those special right triangles because the bottom number is going to be 3. That's fine. It's a negative, so we're going to be rotating in a clockwise fashion. Which quadrant do we end up? This one right here. It's definitely past pi over 2. It's definitely before a half circle pi. Half circle negative pi, I mean. So we are basically in quadrant 3. Sketch out the triangle real quick. It's like this-ish. We have a negative adjacent. We have a negative opposite. But we're concerned with the cosine, which is just adjacent. So what kind of triangle is this? Again, it's going to be a 30, 60, 90 style. The 3 is on bottom. So 180 divided by 3 is 60. So this is going to be 60 degrees. So this one is negative 1. Hypotenuse is going to be ratio 2. So negative 1 to 2. Well, actually, yeah. Let's change the argument, of course. Changing it to a positive argument. What if we had done instead cosine of 2 pi over 3? So that's going to be positive argument. So that's counterclockwise rotation to generate our reference triangle. So we're past pi over 2. We are before half circle. So we're somewhere in quadrant 2. This is going to be 30, 60, 90. So 180 divided by 3 is 60. So the 60 is here-ish. Well, the ratio is going to be negative 1 to positive 2. So negative adjacent relative to hypotenuse is 1 to 2 with a negative because we're going to the left of the x-axis, which is the negative values. So that should be final answer. Tangent now. So we have tangent of 5 pi over 6. What is that? You see how the 5 is almost a 6? So we know this is going to be in quadrant 2 because we're going counterclockwise almost to half circle. But 5 is not 6, so we're a little bit short. How much short are we? We're short by this much. How much is this much? It's pi over 6, that much. Because again, if you added this 1 more to this 5, it would have become 6 pi over 6, which is half circle. So right there, make note of the signages. This is going to be 30, 60, 90. So this is going to be the intermediate side, which is going to be negative root 3. And the opposite is positive 1, because tangent, we only care about opposite and adjacent. So the ratio of opposite over adjacent is going to be negative root 3 over 3, rationalized. Next up, we have sine of negative 7 pi over 4. 4 is on bottom, so that's our favorite 45, 45, 90. It's negative, so it's going to be clockwise rotation. It's almost an 8, because if you double 4, and this had been an 8, that would be full 360, full rotation. But we don't have 8. We're a little bit short of a full rotation. It's only 7. How much short? We're short by pi over 4 of a full rotation from clockwise. Or if you don't like that, you could always do alt strats. If you don't like negatives, right here, you can see that the 7 is not quite 8. Because, again, 8 over 4 would have given us negative 2 pi. That would be full rotation clockwise. Back to neutral position, right? But we don't have that. So we know that to change this into the smallest possible positive coterminal angle, we just need to add 1 full rotation, which is plus 2 pi. Technically over 1, but since 4 is mismatched with 1, multiply top and bottom by 4. So times 4 to the bottom and times 4 to the top. So thus, when we add those two, we get the coterminal angle. That's pi over 4. So very nice, very clean. So now that it's a positive angle for the argument, it's just going to be counterclockwise rotation by 45 degrees. So right here, drop down to the x-axis. The ratio is 1 to 1 to root 2. Everything's positive because this is quadrant 1. Positive x direction, positive y direction. What are we doing? Sine, which is opposite over hypotenuse. What over root 2? AKA root 2 over 2. Final answer. Moving on, we have tangent. Tangent of what? 11 pi over 3. So a couple of things to make note of. If you double the 3, you get 6. That would be full circle rotation, right? This is 11. That's more than full rotation. So we know that this one can be reduced. So the question is, how much should we reduce it by? Well, that is a handsome question. So if you double this, we get 6 pi over 3, right? So that's just 1 extra full rotation. But if you multiply this by 4, for example, that would be 12 pi over 3. Which 11 is less than 12. So we don't have 2 extra full rotations. So just subtract 1 full rotation to find a coterminal angle. So this is a positive argument for the angle input. But to make things easier for ourselves, we're going to subtract 1 full rotation, which is minus 2 pi. Just make sure we match the denominator. So top and bottom times 3, thereby getting 6 pi over 3. And that's all we have to subtract from that one. So that's going to give us 5 pi over 3, which is the smallest positive coterminal angle. That's what we want usually. And now we get started with the problem. So it's a positive argument, so that's going to be counterclockwise rotation. 5 exceeds 3. In fact, 5 is almost double of 3, so that means we're in quadrant 4. What kind of triangle are we doing? We're doing 30, 60, 90. The 3 is on the bottom, so 180 divided by 3 is 60 degrees, so it's like this. So this reference part, that is pi over 6. Wait, why am I doing pi over 6? I'm sorry, pi over 3. Yeah, pi over 3. Because again, 5 is 1 short of a full 2 pi rotation. Since we know this is going to be 60 degrees, then basically the ratio is going to be, the opposite is going to be root 3. But remember, it goes down the y-axis, so negative root 3. to the right of the x-axis, so that's +1, and then that's all we need because we're dealing with just tangent. So we don't care about the hypotenuse. So the ratio of tangent, the tangent gives us opposite relative to adjacent. So -√3/1, just make it a clean -√3, final answer. Or rather, this is the original problem. There you go. All right. And now we're going to do the mix-ups with the, what are those called again? Interquadrant angles as well. So cosine of now pi/2. So that's going to be the small one. So we don't need to do any subtraction shenanigans from this one. So how do we know this is an interquadrant angle? Because the bottom is not one of our favorite numbers, which again are 3, 4, and 6. This is a 2. So thus interquadrant angle. Which interquadrant angle are we dealing with? We're dealing with the upwards one, the 90-degree one, which is from here to there. So what kind of quote-unquote triangle have we formed? It's the collapsed one with no adjacents, right? The adjacent is 0. And since we're dealing with cosine, it's going to be adjacent, which we just acknowledged is 0, over hypotenuse, which is going to be not 0. So we can evaluate that. It's going to be equal to 0. Well, then we're done. So cosine of pi/2. The ratio is 0 to not 0. All right. Tangent. 2 pi. And 2 pi is exactly full circle, right? So 0 is going to be neutral, no rotation, and then 2 pi is 1 full rotation. So a full rotation takes us back to neutral position, so tangent of 0. So it's as if we didn't even rotate at all. So we're in standard neutral position right here, where there's a collapsed triangle, again, quote-unquote collapsed triangle. There's no opposite, because if you rotate, then you will get an opposite, right? But we didn't rotate, essentially, so no opposite. Opposite is 0. The adjacent is not 0, so opposite is 0, and adjacent is not 0, which we can evaluate, so we're going to get 0. Final answer. Final answer. Alright, let me start check marking off some things so I don't accidentally redo them. And then we have, next problem up, we're going to have cosine of 100 pi. That's definitely extra rotation, so this is being super extra. But how extra is it being, right? You don't want to sit there and just keep subtracting 2 pi over and over, you know what I mean? Because that's a real pain. So instead of doing 1 by 1 subtraction, you just do division real quick. So the question is, how many full rotations fit into there, right? So if you divide by 2 pi, 100 pi divided by 2 pi gives you exactly 50 of those 2 pi's. So we have 50 full circle rotations to generate our triangle. Since we have 50 of those, essentially what happens is we're just going to reset to neutral position. So again, if we take away 50 full circle rotations, it becomes 0. So in essence, our problem, we're just doing a collapsed triangle yet again. So 0 means neutral position, because we're biased towards right-hand side, which means that we have no opposite, but the adjacent is the same length as the hypotenuse. So for this one, it's going to be adjacent, which is equivalent magnitude to the hypotenuse. So it's a 1-to-1 situation, so the answer is just going to be 1. So there it is, and we are good. Hold on. Roommate's texting me about dinner plans. Okay, we're back. Previous problem we had just finished was the cosine of 100 pi. What are we looking at now? We're looking at sine. We are evaluating sine of negative 15 pi over 4. That is one of our favorite situations because it's a 4 in the denominator. Again, it's one of those 3, 4, or 6 situations. So that's the 4 one. So it's going to be the 45, 45, 90 triangle. So no inner quadrant this time. We're looking at this one. If you double the 4, it's going to be 8, and 15 exceeds 8. So this one can be reduced to get a nicer, cleaner coterminal angle. It's a negative as well. By how much, though, right? So if you double 4, that's 8. 15 is greater than 8. But if you quadruple this, right, times 4, you get 16. So this is below 16. So we just need to take away one full rotation. So plus 2 pi is going to be one full rotation. That's a fraction. Top and bottom times 4. So it's plus 8 pi over 4. So we can rephrase this problem into sine of negative 7 pi over 4. Which I'm perfectly content with. So we can treat this as a clockwise rotation. It's not quite full circle. It's 1 pi over 4 short of a full rotation clockwise. So that means we're in quadrant 1, like that. Because again, 7 is 1 short of 8, which would be full rotation. So again, quadrant 1 with a 45, 45, 90 triangle. The ratios are 1 to 1 to root 2. Everything's positive in quadrant 1. So therefore, signage, you just take opposite over hypotenuse. Root 2 over 2. Eventually, you just get so used to these ratios that you automatically rationalize them. Or if you memorize unit circle, they're already rationalized for you. I think they are. I forgot. But that's that. Oh wait, before we conclude on that one, this is going to be a negative argument, but if you don't like negative argument, you could always add one more 2 pi to this one. So plus 1 more 2 pi, which is 8 over 4. So once you do that, you see that becomes sine of pi over 4. Positive now, which means we are in quadrant 1. What kind of triangle? 45, 45, 90. What are the ratios? 1 to 1 to root 2, all positives. Sine is what? Opposite over hypotenuse. So root 2 over 2. Same answer as it should be. Next up, we have tangent. Tangent of what? Negative 41 pi over 2. What kind of triangle do we end with? Well, look at the denominator, right? It's denominator 2, so it's going to be one of those interquadrant angles. Which one is it? Well, if you double 2, that's 4. This is already greatly past 4. It's 41. That's okay. We could just simply, what can we simply do? We just kind of figure out how many full circles we have in there, right? Well, by approximating this one, it's close to 40. So it's going to be 40-ish divided by 2, which is 20-ish. How many full circles, how many 2 pi's can we fit into those? We can fit approximately 10. So we have about 10 full circle rotations, right? So we need to add 10 full circle rotations to get to a nicer value for the argument. If you care to do that, of course. Alright, so what is that? What are we adding? We're adding 20 pi. That's not matching denominators. So top and bottom times 2 times 2 times 2. So what's negative 41 pi plus positive 40 pi over 2? It's going to give us negative pi over 2. So again, just changing it from a larger magnitude to a smaller magnitude. It's negative. I'm perfectly content with negatives, and I suggest you can build up some more practice with negatives as well so you get comfortable. Where exactly are we? We're now moving clockwise, interquadrant angle, so it's going to be the first one we encounter. So this one. So it's the downwards interquadrant angle, downwards. So negative for the opposite. What does tangent give us? It gives the ratio of opposite, which exists, over adjacent, which is a collapsed triangle, which is 0. So we have 0 over not 0. That's just going to give us 0. And we're done. That's it. Alright, so fun times. That's going to be the majority of those type of nonsense you're going to be working on. And I think at this point there's going to be, we're going to move on. So far we've covered angles. We've covered trig problems where the argument magnitude is greater than pi over 2 or less than 0. Greater than 2 pi or less than 0 for the magnitude. And then after that we covered the interquadrant angles, and then now I think we're to be going quote unquote backwards. And here's what I mean. If you consider something like this, sine of pi over 4, for example, and then you get some sort of ratio. If you count this as going forwards, then we're going to be going backwards. So we are essentially considering the idea of inverse, but we're not quite there yet. What I mean is we're not going to be doing this, that's sine inverse, or if you prefer arced sine. So we're not quite doing that just yet, but we're virtually doing it. Let me think if it's a good idea to get started on this right now. Yeah, I think we can get started, and we'll just do feature streams, which is going to further elaborate on these basic concepts first. Later. So again, going forwards goes versus going backwards. Going forwards function, again, that's if you're going to the store, you buy something. Well, since Black Friday is coming up, right? You go to the store, that's the forward function. You put in money, that's the forward function. You get a TV, that's the forward function. Backwards function, how did you get that TV? Backwards function. You went to the store and put in money, right? I guess kind of backwards. The true inverse, okay, let me write this down symbolically. So this is the forwards function. You go to the store, you input in money, and then you get your TV. That is forwards function. So officially, if you're doing inverse function, then you go back to the store, which is store inverse. You return the TV, and then hopefully you get your money back. And not some sort of rebate or something. You actually get your money back. So that's quote-unquote forwards function, and then this is quote-unquote inverse function. And like I said, we're not exactly doing this one. We're virtually doing it. So if you saw that you have a TV in your hand, that means that you knew how much money you spent on it. Theoretically, right? If you see the model and make of the TV and you look at the advertisement, and that's the TV that you got, then you should be able to figure out how much money you put in to get that TV, right? And here's what I mean. Going forwards, again, if you take sine of pi over 4, then you get a ratio of root 2 over 2. But I'm going to leave this in irrational denominator form. So let's leave it like this. So this is the ratio of opposite over hypotenuse. So again, forwards function. You inputted the angle argument, and then the function outputs the ratio of opposite over hypotenuse. Forwards. Start here. End with this. But what if you don't know what was inputted, but you know what you got out? And now it becomes kind of tricky. And this is where the problem with inverse function, at least for trig functions, what happens in these ones. It's kind of ambiguous. Here's what I mean. Well, so let's actually draw the quadrants real quick. So xy axis is quadrant 1, quadrant 2, quadrant 3, and then quadrant 4. So what kind of triangle that we're drawing on this system right here will give us a ratio of opposite of 1 over hypotenuse of root 2? Well, most people by default will recognize that the triangle could be here. So if you have a 30, 60, 90 right here, this opposite is positive 1, and this hypotenuse is root 2. So how do we get this one? From this one. What angle is that one? Well, isn't it just pi over 6, aka 30 degrees? Yes. Here's the problem though. That's not the only triangle that you can draw in this system that will get you a ratio of 1 over root 2. And here's the other one. Since we are considering a positive opposite, for quadrant 2, there's also a positive 1 opposite for a reduced ratio. So here's that other triangle that could possibly give us an opposite of 1 over hypotenuse of root 2. But the question is, what angle is that? That's still the 30 degrees, right? But remember, this is just a reference triangle. The true angle is from here, neutral position, to right there. So the true angle is short 30 degrees of a full half circle, right? So again, if you like degrees, this is going to be 150 degrees. What does that mean? It means that if we input 150 degrees as an argument into our sine function, it will give us a ratio of 1 to root 2. How do you know which one's which, right? Is the answer going to be this first one that we found? Is it going to be 30 degrees, aka pi over 6, or will it be 150 degrees, aka 5 pi over 6? Which one is it? And the answer is, it could be either of those, right? So here's what I want you to look at. It's going to be, if you're wondering why there are two potential answers, it's very similar to square root situations. Suppose you have x squared is equal to positive 9, right? This situation. You have to ask yourself, well, what number squared will give us 9? And then the most straightforward operation is just take square root of both sides. So square root gives you x, square root gives you 3. But that's even powered exponent, which means we have to contend with plus minus shenanigans, because a negative 3 squared will get you 9. Positive 3 squared gets you 9. Which of those two was hiding inside this x that gets squared? You don't know, so you have to account for both of them. So the answer could be plus or minus 3. And by the same idea, because this one could get you a 1 over root 2 ratio, as can that one, you have to report those ones. Or your answer in this situation. But unfortunately, there's even more than that. So if you report just 150 degrees or just 30 degrees, you still will not get full marks for the situation if you're getting graded, right? And here's the reason why. Because of coterminal angles. And we've already covered that, right? 30 degrees will get you this ratio. But here's the thing. So would 390 degrees will also get you this ratio. Because 390 is coterminal with 30 degrees, which gets you the same ratios in the end. Because you end up in the same triangular location for the rotation. But here's the thing though, it's also coterminal with 750 degrees. So how do we write this? We seem to have an infinite amount of coterminal angles. How can we represent that with our answer for the situation? And it's actually pretty simple. So you start with your base angle. 30 degrees is the most obvious one that will get you a positive 1 over root 2. And you just need to account for all the potential variants of this 30 degree, not variants, all the coterminal angles to this 30 degrees. So for every type of 360, full 360 that you add or subtract, that will take you to a coterminal angle. So you just put a k in it, where k is an integer. So in other words, if k is 0, then you're starting off with the base 30 degrees, which we've already acknowledged. If k is equal to 1, then you're adding 1 full extra spin to get back to 30 degrees. So we've accounted for positive multiples of 360. But if k is negative 3, for example, we're also accounting for the negative spins, the clockwise spins, that still get us to 30 degrees in the end. So what that means is we've accounted for 30 degrees in all angles that are coterminal with this 30 degrees. And we represent it with this answer. So any of the values, for any of the k's that we pick, and we slam dunk it back in here into the function, then we're guaranteed to get a ratio of 1 to root 2. So we've accounted for the 30 degrees and all its possible coterminal angles. We now need to account for the 150 degrees and all its possible coterminal angles. So if you have 150 degrees, plug it in. We end up in quadrant 2 with this triangle as reference. But we need to get all the coterminal situations. So copy paste the same strat. So it could be plus all the multiples of 360, including the negative multiples, right? And once you have it written like this, you've accounted for 150 degrees and all its all its coterminal angles. And if you put 30 degrees plus 360 degrees times k, where k is an integer. Then we've accounted for 30 degrees in all its coterminal angles. And this is going to be complete answer for this one. So, kind of a doozy, but it takes some getting used to, of course, like most things, right? So let's just look at another one, another example. So if you're doing cosine, if we're doing cosine of something like, what's it? 7 pi over 4. This is again going forwards. What are we doing? Well, starting off at neutral, and then we're rotating it almost full circle, but not quite full circle. We're short by pi over 4. So that's going to be our reference angle right there. This is going to be 45, 45, 90 degrees. The ratio is -1 here, +1, and then √2 right there. Cosine doesn't care about this opposite. Cosine just cares about adjacent over hypotenuse. So I'm going to leave it in irrational denominator. So, going forwards, going backwards. What if you don't know the angle that got us this ratio? So, what angle here, if you input it, will give us a ratio of 1 over √2? Again, the most typical one that people first think about will be the one in quadrant 1, since that's where you have a positive adjacent. So +1 adjacent, positive √2 hypotenuse. If you recognize the ratio, it's 1 to 1 to √2, so it must be 45, 45, 90. So 45 degrees, aka pi over 4. And of course, you notice that's not the original angle that we had reported, right? The going forwards, we inputted 7 pi over 4, not pi over 4. So that's again, that's the issue of going backwards. So that triangle as a reference, pi over 4 with the reference angle, it can give us a ratio of 1 over √2, but that's not the only triangle that can give us that ratio. It has to be pi over 4 in all its coterminal angles. So pi over 4 is the base angle. What are all its coterminal situations? It's going to be plus for every full circle, which is 2 pi. Not 360, because now we're doing in radians. Depending on multiples of 2 pi, so times k, where k is an integer. So it could be positive, could be negative, but it will be whole subtractions or additions of 2 pi, which is basically extra rotations, but will still get you to the same base of pi over 4. So those are all the possible situations, coterminal angles with the pi over 4. But as mentioned before, that's not the only triangle that can give us a ratio of +1 over √2. Positive adjacent, other situation, right? With a negative opposite. But again, cosine doesn't deal with opposite. So that's why this -1 is ignored. So what angle is this one? It's going to be, it would have been full circle, right? But minus the pi over 4. Which gives us 7 pi over 4, which was the original angle that we used to go forwards to generate this situation. So this one. So inputting 7 pi over 4 will give us this ratio, but this is only one particular angle that will give us this situation. We have to account for all possible coterminal angles that if you input here, will give us this ratio. So pretty much the same strat as before. You start with the base angle, which is 7 pi over 4. And then we account for all the possible coterminals by adding full circle spins, which is 2 pi. And all their positive and negative multiples. Okay. K is an integer. So all the possible situations number 1, all the possible situations number 2. And that will be the answers we will report if we're trying to say what this value of theta could be. And we'll just run through a few tests just to quote-unquote verify the situation, right? So if you just take pi over 4 as a base and you slam dunk it into there, we end up with this triangle. Blue triangle, which is adjacent 1 over hypotenuse root 2. Which is consistent, yes. And just to show that it works, what if k value is -2, for example? Then we're going to be inputting pi over 4 plus -4 pi over 1. Make sure we match those up. So times 4 times 4. So this becomes -17. I'm sorry. -15 pi over 4. So that's just being extra from the base pi over 4. So this is going to be pi over 4. And then coterminal to that, that's going to be 1 extra spin. I'm doing counterclockwise spin. Whoops. So from this base pi over 4, we're doing clockwise spins. We're doing 2 clockwise spins. So here's 1. And then there's 2. So we still end up in pi over 4, which would still give us the same ratio as before. So it's still going to be the same ratio. Okay, so we're good with that one. Okay, no more undos, I'm sorry. That's fine, ignoring. You know what? Let me just leave the work. So we verify that one. Verifying this one as well, 7 pi over 4. Let's do it for k is equal to +3, for example. Because again, 3 is an integer. Don't put fractions here. So that will be 3 extra spins, but we should end up at 7 pi over 4. So here is 7 pi over 4 again. We're doing 3 counterclockwise spins. So from this 7 pi over 4, here's 1 counterclockwise spin, 2 counterclockwise spin, and then 3 counterclockwise spin. We still end up at 7 pi over 4. That's basically a 45, 45, 90, 45, 45, 90. What's the ratio? Cosine is going to be adjacent 1 over hypotenuse of root 2. So it checks out. So both answers seem to be good. And we are good to go. Let's do some problems. Again, pretty standard problems, standard introductory problems. Let's do sine of pi as equal to root 3 over 2. So now I didn't even bother to show you what angle I put in here to generate this problem. I'm just going to give you the output straight up. So we have an output of root 3 over 2. So in your mind's eye, or on the side of a piece of paper, you could just sketch this out. What situations can we get a positive root 3? Well, you're looking above the y, going upwards on the y-axis. So this is going to be a positive, and this could be a positive. So here's the origin, right? So if we put a positive root 3 here, that's one possible scenario over hypotenuse 2. And here could also be a positive opposite hypotenuse of 2. So the only difference is this is in quadrant 1, so that's going to be a positive adjacent, which we're not concerned with. And then this one is quadrant 2, which is a negative adjacent, which we're not concerned with at the moment. But it's just to show that this triangle can satisfy this ratio, and that triangle can also satisfy this ratio. And they're not coterminal to each other. So this one is a standard pi over 3. This one as a reference angle is pi over 3, but that's not the angle. the angle is from here to there, which is 1 pi third short of half the circle. So red angle is full pi minus the leftover. It's just short pi over 3, which is going to give us 2 pi over 3. So that's the base angle for the triangle in quadrant 2. So that means that this theta here, it can be equal to 2 pi over 3. So that one through this one, right? To generate this reference triangle right here. But that's just one. We need to capture all the answers, so all coterminal angles to this one. So what's coterminal to this one? Just account for it by adding extra 2 pi's. How many 2 pi's? Well, it depends on what you want to pick. So we're gonna put k right here, where k is an integer. So we have to put this. If you don't put this one right here, then k could be anything, including fractions, including irrational numbers. We only want variations of whole number variations and their negatives with the 2 pi. Just to reiterate. So this one should capture all the possible scenarios that end up in quadrant 2. That will give us this ratio. And now we just need to deal with the triangles and all their coterminals that happen in quadrant 1. We already know this is pi over 3 as mentioned before. So if we input pi over 3, then we will generate this 30, 60, 90 with the correct orientation with the root 3 on the opposite. And the hypotenuse is going to be 2 for the ratios. That's the base angle. We just need to get all the coterminal angles, so plus 2 pi k. Where k is an integer, as stated before. And that's it. That will capture all the answers that will satisfy this sine function that will give us a ratio of root 3 over 2. And of course, moving on to other problems. What if we're doing tangent of something? We don't know what that angle is, but that's going to give us a ratio of -1. That's just a one number, right? But technically, you can always put it over 1. So it could be -1 compared to 1, or 1 over -1. Because this negative is ambiguous. So you can put it in the numerator, or you can put it in the denominator. And you can bet that that's going to be conducive for finding triangle number 1 and triangle number 2 situation. Okay, so what triangle could possibly give us this ratio or this ratio? So let's do this one first. No, yeah, let's do this one first. So the opposite ratio to the adjacent is they have the same lengths. One of them goes up and then the one goes backwards. So opposite is on the y-axis. It's positive in the y-axis, but it's negative on the x-axis. So these two are both positive y's for the coordinates. This is positive x, so we're not dealing with this quadrant. We're dealing with that quadrant. Because it's -1, you're going to the left of the x-axis, on the x-axis. So we're dealing with this triangle right here. 45, 45, 90 for the reference, because there's a -1 ratio for the adjacent to the +1 hypotenuse. I'm sorry, opposite. So -1 adjacent to +1 opposite, which gets us this situation right there. So let's color code that as red. Red will take us right there. Pi over 4 is the reference angle. That's not the angle we're truly dealing with here to get this ratio. It's going to be pi over 4 short of a half circle. So just do the subtraction. If you haven't memorized it, it's 3 pi. I'm sorry, it's 3 pi over 4. From here all the way to here. So the situation that will give us this ratio of positive 1 opposite to negative 1 adjacent. That one arises from 3 pi over 4. That's the base angle. We need all the coterminal angles, so plus extra spins based off of integer k. So we have taken care of all possible triangles in quadrant 2. We now need to just deal with triangles and their coterminals in quadrant 1. See, there's a negative, oh, I'm sorry, not quadrant 1. Oops, thank goodness. I double checked this. Not this one. That's a negative 1 opposite. That's a positive 1 adjacent. So the positive 1 is on the x-axis, and then the negative 1 is on the opposite, so downwards. So we're actually in quadrant 4, not quadrant 1. I'm sorry. Quadrant 1 will be positive up on top and positive up on bottom as well, down on bottom as well. So we're actually in quadrant 4, because that's a downwards opposite and a forwards adjacent. So what angle is this? Well, let's keep the positive answer. So that right there is 1 pi over 4 short from full circle. So just do the math to get the whole blue. So times 4, so we have 7 pi over 4. That's the base angle starting from neutral. That takes us to this reference triangle right there. That's 7 pi over 4. That's only one angle. We want all the other ones as well. So it'll be plus 2 pi and all its possible multiples and their negatives. Okay, isn't it? Answer number 1. Answer number 2, and that should give us full marks if we're being graded on this situation. And that solves this scenario. That's done. Alright. Occasionally, just to make problems a little easier for people, or for students, sometimes wait, I'm saying students aren't people. I mean, well, you know what I mean. Sometimes the problem has something called restricted domains. So let me show you what I mean by that. So in the situation where you're given nothing, right? So if the problem opens up as cosine of some angle we don't know what it is equal to root 2 over 2, and nothing else is written, then this one you need to report angles and all their possible coterminal angles. But certain problems you will see domain restrictions. So basically we will be able to narrow the scope of our answers. So here's what I mean in terms of the notation. So theta, it's not just any theta. We're going to narrow our search to all the thetas that are between 0 and 2 pi. So basically just one full rotation, and those will be the only, let me think how to phrase this properly. Well, basically we don't have infinite answers anymore. We just have 2 answers in this situation. So let me show you what I mean. We're going to open up with the same moves pretty much. What can give us a root 2 over 2? Well, this one I'm going to change it into into irrational denominator first. It's just going to be the situation. Cosine is adjacent 1. So that's a positive 1 adjacent. And we have 2 variants. We can have the root 2 leading into quadrant 1, or we can have the root 2 leading into quadrant 4. Keep your hypothesis positive. So the difference is this one has a positive adjacent. Positive opposite. And this one we have a negative opposite. but cosine doesn't distinguish between those two. This is why we need to get both answers from quadrant 1 and quadrant 4. So let's answer quadrant 1 first. So what angle here will give us an adjacent 1 relative to hypotenuse of root 2? This is where you memorize your right triangles, special right triangles, or you reference your, what is this called? Reference the, my brain. It don't work sometimes. The, what's it called? The chart. The unit circle, I'm sorry, unit circle. So now I just like to memorize these special right triangles. So which one is that one? It's going to be the 30, 60, 90. Since the 1 here is adjacent, then this one's going to be the 60, or pi over 3 situation. So in quadrant 1, how do we end up this angle? If we have a base angle of pi over 3. We now have restrictions, because normally we would put like plus all the extra coterminal angles, right? But here's the thing though, if k is equal to positive 1, we're going to get this, which is past our viewing window, past our restriction. This little clause here tells us that our answer, theta, should be between two values, between 0 and between 2 pi. If you're adding 2 pi, that's taking us past this restriction point. So why are we even bothering to add it? If you subtract 2 pi, because k is like -1, for example, that'll take us below 0, which is also past our area of consideration, past our restriction point. So for this situation, we could just simply omit this one. We don't need this one. We only report this answer, because this pi over 3 is the only type of angle in this quadrant 1 that will lead us to this particular ratio. Only pi over 3. If you add 2 pi again, it'll take us to this one. But adding 2 pi takes us past this restriction, so we have to exclude all those answers. So in this situation, keeping this one right here will be a detriment. You'll be deducted points if you put this one right here, where k is an integer. So for this situation, we omit that because of the restrictions. Alright, so that takes care of quadrant 1. What about quadrant 4? Which can also give us a ratio of adjacent of 1 over hypotenuse of root 2. What angle is that? That's going to be this one. So again, this one is going to be pi over 3 as the reference, which means that we are pi over 3 short of reaching full circle 2 pi. We would have reached 2 pi, but we are short pi over 3. So mathematically, what does that become? 6 minus 1 is equal to 5 pi over 3. So that's the scenario that will lead us to this triangle happening in quadrant number 4. And again, typically, if we had no restrictions, no domain restrictions right there, we weren't narrowing our focus, then this one will have to be plus 2 pi times k. But because we have this domain restriction, we're cutting it off at 0. Anything before 0, anything after 2 pi, we're going to ignore them. Adding or subtracting 2 pi will take us well beyond these borders. So as such, we don't need to include this part. So this answer will be all that we have to report. So answer number 1. And then answer number 2. Either of those two will get us, if you input this one into here, or if you input that one into here, it will give us a ratio of 1 over root 2. And those are the only 2 answers for the situation. Only 2 answers, not infinite answers. Let's run over another example. So we're looking at cosine. No, let's not do cosine. Let's do tangent, actually. Yeah, tangent. So tangent of theta, we don't know what this angle is, but we know that we're going to get a ratio of root 3 over 3. However, we don't care for any answers. We care about answers. The angles have to be between 0 and pi. So the angle that we care about is between 0 and pi. You notice I changed it. It's no longer 2 pi, so be careful. Always pay attention to the restrictions. Very easy way to lose points, right? Alright, so this is just detective work. Again, we're not given the angle, we're given the ratio. And tangent is simply opposite over adjacent, right? This one is, I prefer to have it irrational on the bottom, so I'm going to change this into 1 over root 3. Alright. So tangent, what angle could possibly give us a ratio of 1 over root 3? Well, the easiest one to find, again, is typically in quadrant 1. Because we have a positive one opposite over, that's the opposite, over adjacent root 3. So the question is, what angle will get us to this particular triangle situation in quadrant 1? It's going to be classic 30, 60, 90. The 30 opens up to the small one, so this must be pi over 6. So again, what could get us this ratio if we inputted pi over 6? Let's call that the green situation this time. So for the green situation, the input, it could be pi over 6. Do we need to account for all the coterminal angles by adding 2 pi k? No. Because if you even add just one extra 2 pi, it's going to take us past pi. So that's outside of our consideration. If you subtract 1 2 pi, that will take us past this one, which is also outside our consideration. So for this particular problem, we only report this one, and this one is dropped. So let's ignore this part. So only one answer that ends up in quadrant 1 right here. But here's the thing though, that's not the only triangle that will give us this ratio of 1 to root 3, right? Because here's the thing though, if we have a -1 ratio in the ratio to also negative root 3 right here, you see how the negative here cancels the negative there to produce positive 1 over root 3? That means that having a triangle in quadrant 3, where you have a negative root 3 adjacent, and then a -1 opposite, that also gives us this ratio. So the question is, what angle leads us to this reference triangle? Again, it's not pi over 6. We could kind of steal our work, right? This is pi over 6, and the reference angle here is also pi over 6, but this is not the true angle. The true angle is from neutral all the way to this one. So what is that? We're pi over 6 past half circle. So pi over 6 past half circle. That's just 6 over 6. So we're going to get 7 pi over 6. Which gets us to, from here to there. So 7 pi over 6. And if we consider all coterminal angles that are possible, 2 pi k, right? So this is the default generic answer if you have no domain restrictions. but we do have restrictions. Again, can't get past pi, can't get past 0 in the other direction. So this one is superfluous, so extra. We don't put these ones. 7 pi over 6 though. You notice that this one changed, remember? It's not 2 pi anymore. It's just half circle pi. Well, 7 is past 6. So this answer is also outside of our consideration. It's past pi. So this one, we don't report this one either. Which means there's only one answer. This is the only answer that we're considering for the situation because it falls within domain right here. This is always specified by the problem. Unless the problem is poorly written, you will always have specification. Moving on to the next example. I should just use this one, huh? Okay. Well, regardless, moving on to the next situation, we have sine of sine theta, some angle. We don't know what angle it is, but it will give us a ratio of 3 over 2. Additionally, we have domain restrictions. We are only considering angles between 0 and pi, yet again. So same consideration as the previous problem. Will give us this. Alright. Just sketch it out. Rough, very rough sketch. You don't need to be super accurate. So we have positive opposite of root 3. So here we could have a positive root 3 opposite in quadrant 1. And then we could also have a positive root 3 in quadrant 2. So this is one triangle that will give us a situation. And then this is the other triangle that could give us the same ratio. So we just need to consider what angle will take us there, right? So let's consider green first. So what angle will take us from here to here? Well, what's the reference angle, right? If you memorize these ones by now, this is going to be pi over 3 for the reference. So in other words, we're pi over 3 short of reaching half circle. Pi over 3 short of half circle. So that's going to be 2 pi over 3. From here to there. And it is within domain restriction. So if we answer 2 pi over 3, 2 is short of 3, so we're well within domain restrictions. So yes, we report this in. But we don't need to, again, we don't need to put this one. We don't need to put plus 2 pi k because this restriction, adding this one will take us past our restrictions. So omit that. So that's scenario number 1. What about scenario number 2? I'm going to color this one teal. Oh, that's not teal. Whatever blue this is. It's baby blue. So what takes us from here to here? It's going to be pi over 3. That's also within domain because this is 0 and this is pi. And pi over 3 is well before this. We don't need to consider the coterminal angles because adding 2 pi will take us past here. Subtracting 2 pi will take us past there in the other direction. So thus, we only report this one. And then we're done. So those two angles will, if we input them into the function, either of those will give us this ratio, which is what we want. And they both fall within restriction. So we're good to go. But let's change the restriction just a little bit for this problem, right? What if for this problem, let's change it. Let's be more annoying, right? What if we have negative pi over 2 and we have positive pi over 2? For the most part, it's the same thing. We're still going to have the same base angles to consider as before, okay? So how do we get to quadrant 2 if we move counterclockwise by 2 pi over 3, it will take us to quadrant 2, which will give us the right ratios for the situation, right? But 2 pi over 3 is past our viewing window, which is pi over 2. So just compare it, right? Compare this one to this one. How do we know it's past? Well, just do a comparison, right? Compare this one to this one. Put the little box of comparison between those two. Cross multiplication, that gets us 4 pi. Cross multiplication, this gives us 3 pi. 4 pi is past 3 pi. So this one is past our consideration. So, no. So going this counterclockwise direction to take us to quadrant 2 takes us outside of restriction. But that's going counterclockwise. What if we went clockwise, right? Will that take us... Alright, let me rephrase that. What if we go clockwise? Can we still get to this quadrant 2 triangle and still be within restrictions? Let us see. So moving clockwise, we are now dealing with negative situation, right? So what negative angle will take us from here all the way to right here? It's going to be a half circle clockwise, but you got to push past half circle by pi over 3. So half circle clockwise, but pushing past by pi over 3. So if you simplify that, that's negative 4 pi over 3. That's the base angle that will take us from here all the way to there, quadrant 2. Is this within a restriction? No, it's not. So negative 4 pi over 3 is well past negative pi over 2 in the clockwise direction. So this one answer is omitted. So there are no triangles in quadrant 2 that falls within this restriction. So thus it's omitted. So we obliterate this entire quadrant. It's gone. Okay, that's gone. But we still have the other one, right? We still have pi over 3 to consider from our previous situation. Pi over 3. That will give us a ratio of root 3 over 2, which is what we're looking for. The question is that within our restriction? Is this between that number and that number, right? Well, it's positive, so it's definitely past this one. But is it before pi over 2? Just do cross multiplication. So we're comparing this one to pi over 2. If you don't remember your division, this is a larger number, so this whole thing is smaller than this one. Well, just in case, you could always cross multiply. So this one becomes 2 pi on the top, and this one becomes 3 pi on top. 2 pi is less than 3 pi. So yes, this one was within our domain restrictions, but not by, just barely, right? So we don't even need to consider the other situations. So if you plus 2 pi k, either adding extra 2 pi's or subtracting extra 2 pi's will take us past both of these restriction walls. So pi over 3 is the only answer for the situation given these restrictions. So again, the only answer for this, pi over 3. Let's consider some other situations. Suppose we have cosine of theta, some angle we don't know what theta is. However, we do know that the outputted ratio is going to be negative root 2 over 2. We do have restrictions. The restriction is going to be from 0, including 0, all the way to 2 pi. So we probably have two answers in this situation. So here's the problem. Again, I don't like having this situation with the radical on top. I just like to keep it irrational on the bottom. So it's basically like this. This is technically ambiguous, right? Because this negative in front, it could be either on the top or it could be on the bottom. But since this is cosine, we only consider it on the top. Okay, good. So this negative, don't put it on the hypotenuse. Never consider it on the hypotenuse. You almost never have the negative on the hypotenuse. So we'll put it right here. So what can possibly give us this scenario? Let's see. Sketch. So we want a negative adjacent. And the only time we get negative adjacents if we're going in the negative x direction. So there are only two triangles that could possibly give us a situation. We can have this triangle like this, because that's a negative adjacent, or we can have this triangle right here, which also is a negative adjacent. So thus we can have a triangle in quadrant 2, or we can have a triangle in quadrant 3. That gives us ratio. So let's fill it out. So we want a -1 adjacent for the ratio. It's right there. And then we want a √2 for the hypotenuse. So √2 or √2. You see how both of these, in conjunction with this -1 adjacent, can give us this situation. We don't care that the opposite is +1 or -1, because this one doesn't figure into the signage of this one. So thus we have two scenarios. So let us deal with case 1. Or I mean, case 1 in quadrant 2. What angle takes us from there to there? We're pi/4 short of half circle, so from here to here must be 3 pi/4. So that's theta consideration number 1. Theta could be 3 pi/4. Do we need to account for coterminal angles? No, because our restrictions are from 0 to 2 pi. So for this one, we don't need to put plus 2 pi k. That will be wrong, actually. So omit those. This one is good to go. And then, of course, for the triangle in quadrant 3, it has to be from here to there. It's going to be pi/4 as a reference angle past half circle. So theta could be pi/4 past half circle. So summing those two up, we get 5 pi/4 as the base angle. Again, we don't need to consider the coterminal angles because this one, the restriction is 2 pi and 0. So to be adding anything, any type of 2 pi's, will take us past the consideration points. So that would be wrong. So delete this. So this is the only triangle, the only angle in quadrant 3 that will satisfy the restrictions here, and that will give us these ratios right there. So that's it, 2 answers. So answer number 1 is 3 pi/4, and then answer number 2 is 5 pi/4. That will give us this ratio and are within restrictions right there. So multiple things to juggle at this point. It does get kind of a lot, but not too bad yet. The really annoying problems is when you have something like this. If you have like a 4, or like a fraction here, these are like the worst type of problems you will get. Like you can get something like this, and it's going to be like 1/√3. I'm sorry, 1/√2. And then you have some funky restrictions. It could be like -pi to pi, for example. These ones are the worst because you have this modifier on the angle right here. We're not going to do these at the moment. Probably reserve that for another stream because I feel that's going to be a lot of information. So again, this one is going to be your worst situations. Because this situation, you could potentially get like 4 or 6 answers. Unlike the 1 or 2 answers we've been getting for the other restrictions. So these are like the worst type of problems. Especially if you have like bigger numbers in the front. If you have like 3, that's also really bad. If you have like a 3 pi right here, 3 times theta, this is really annoying. But we're not doing that. Or probably 2 more problems for this current session, and then I'm just going to call it. So here is tangent of theta. And it's going to give us a ratio of -3. The restrictions. What are the restrictions? Oh, I'm sorry, it's positive √3. Whoops. For my pre-written problem. And then the restrictions are from, let's make it annoying, right? From -2 pi. Watch out for that one. And less than or equal to theta, and then theta is less than or equal to 0. See that one? Extra annoying. Alright. So, well, unfortunately, tangent is supposed to give us a ratio. This doesn't look like a ratio, but you could always manually change it into √3/1. Or, don't forget your negative cancellations. You can have a negative adjacent over negative opposite, because we're dealing with tangents. So scenario 1, scenario 2. Let us consider where those potential triangles lie. That one's the nicer of the two, right? So we have an opposite of √3, positive. Over an adjacent of +1. So this is a quadrant 1 scenario that will satisfy this ratio for this angle. And then for the other possible scenario, we have a negative opposite and a negative adjacent. So negative √3 opposite, and then -1 adjacent. And then that triangle lies in quadrant 3 as a possible scenario. So the question is, what are the base angles that will lead us to these to these two scenarios? So let's deal with this one first. So what angle theta will take us from here to there, right? This is a 30, 60, 90. That's going to be 60 degrees, which is pi/3. So that could be pi/3. That's just the base angle though, so it could be plus 2 pi k, and this will give us all the possible coterminal angles, but we have restrictions from negative angles to 0. This is our base angle. It's positive, right? So this is not going to be your answer this time. So you can't just erase this and call this your answer, because pi/3 is the base smallest possible positive answer, but a restriction is only up to 0. So no positive solutions. So what do? This is where you can kind of use this to help you answer the question. You can actually use this to list off your potential candidates for your answer. So if you have a restricted domain like this one, and it's not too ridiculous, you could just simply list your answers. Build off of your answers from this one right here. Again, the answers that we're considering are all going to be negative answers or 0, right? So we're going to start with negative values of k. So consider -1 for the k, -2 for the k, -3, and more if we need to, right? So if we consider -1 for the k, then we are dealing with coterminal angle, this one, minus 2 pi. In other words, minus 6 pi/3. So that's going to give us an answer of -5 pi/3. Answer number 1. Is that good? Yes. That is definitely between -2 pi and 0. So this base answer is good. Not this one. This one. Alright, so we satisfied this one, and then if we move on to -2 for the k value, so we're subtracting 1 more 2 pi, right? if we consider that, that's actually going to take us past this one, because this is negative 2 pi. So it doesn't make sense to subtract 1 more 2 pi. It will take us past the border. So there's no need to consider anything else. So no. No. This is the only answer that will result in a triangle, reference triangle in quadrant 1. That's it. So we're done considering the possible reference triangles in quadrant 1. What about the ones in quadrant 3? So how do we end up in quadrant 3, right? We can start from here, go into there, right? We can consider the positive angle situation, but if you want to shortcut it just a little bit, we already know that we're not considering any positive angles, because it has to be less than or equal to 0. So if you wish, you don't need to go counterclockwise. You can go clockwise right away. So how do we go from here to there? Well, the reference angle here is pi over 3, so we're pi over 3 short of a of a half circle in the clockwise direction. So half circle, but we're short pi over 3. So in other words, that's going to be negative pi, negative 2 pi over 3. And again, we're starting with a negative base rather than this one right here, because restrictions. You see how this is negative 2 pi? We could probably just end it here. We're not going to subtract 2 pi, because this one will take us well past the border. Nor will we add 2 pi, because if you add 2 pi, that'll take us into positive angles, which we have to be less than 0, less than or equal to 0. So thus we only have one particular angle that will satisfy and end up with a reference triangle in quadrant 3. So this is the only possible scenario. So let's take this one and put it next to here. So 2 answers for this problem. So we have negative 5 pi over 3. Or we have negative 2 pi over 3. And again, those are the only 2 answers for the scenario. Alright, I think I'm going to stop right here. Maybe there's going to be more later tonight. I'm not entirely sure. Or later this evening, or my evening at least. But regardless, the next time we meet up for the trig session, it's going to be with the just further expanding on more problems, just basically doing a bunch of problems with the things that we've covered today. So practice some of these problems, just go over exactly what we're doing, and then next time I'm going to cover more, just like a bunch of problems, and we'll take it from there. So I'll see you in the next one. You have a good one.